Hello, in this video we're going to be talking about particle in a ring model to calculate or estimate what is the minimum energy that is required for an electron that belongs to this pi system in the molecule to get excited. The molecule we're talking about is Coronene, and we're going to make two assumptions to make our life easier. So what are those? First, it's referring to the size of the ring where the electron is moving. And for that, we're going to be using that the size of the ring is roughly 3 times the distance between carbon and carbon that you will find on a benzene. Benzene looks like the structure that we have here right in the core of this coronene molecule. And that has single and double bonds. And remember that because those single and double bonds are conjugated, the distance between carbons that you will find in such a structure is neither going to be double nor single, but something in between. Which, by the way, if you haven't watched the video for the particle in ring system for benzene, where I go over some more details on how to calculate that, and those distances, please make sure to check it out. So 3 times the bond length between carbons we find in benzene, that's we found that it's going to be 140 picometers. So 3 times that is going to be the size of this ring. So which brings me to what ring we're talking about. So the electrons are going to be confined to move only in the periphery of this molecule, sort of like the outer part of this molecule and the blue circle that I'm drawing there. Okay, so with that, we basically are saying we're going to ignore whatever conjugation may happen with this quote-unquote benzene in the center of this molecule. So we're going to forget about that for a moment to make our life easier. So let's count the number of double bonds that we have. Let's start there. Let's go around that circle, and we are counting those double bonds. 1, 3, 5, 7, 9 double bonds. And since each one can have up to 2 electrons, that's going to give you a total of 18 electrons that are forming this pi system, where the energy is proportional to the principal quantum number square. The proportionality constant being the reduced Planck's constant square divided by 2 times the moment of inertia. In this case, it's the electron that we are considering, so the moment of inertia will be calculated with the mass of the electron times the radius square, the radius of that ring where the electron is moving. The principal quantum number belongs to the integers, including 0. So if we are considering 18 electrons, each energy level holding up to 2 electrons, there's going to be 9 energy levels that are going to be occupied. And with that, the principal quantum number that describes each one of those energy levels are going to be 0, plus minus 1, all the way to plus minus 4. The radius is going to be 3 times 140 picometers, and the transitions are going to happen between the highest occupied energy level and the immediate higher level to that, the lowest unoccupied energy level. So it's going to be between quantum number plus minus 4 to plus minus 5. Okay, make the substitutions of all the parameters in my equation for the energy. And remember that we're calculating the difference in energy between those 2 energy levels, the final minus the initial. So that's going to give me plus minus 5 squared minus plus minus 4 squared. All of that multiplied by this proportionality constant that we mentioned before. So 25 minus 16, that's 9 times this constant value. So you can calculate that. You can have that as a reference for whenever the energy levels where the transitions are happening are different, but these values are constant, so you have them as a reference. So when you finish the calculations, you punch those numbers on your calculator. The minimum energy required for an excitation in the system is roughly 3.11 10 to the minus 19 joules, which, by the way, again, I invite you to look at, to check out the other video where I did similar calculations for benzene, and that's pretty much it. We are done with the estimation of this transition energy. The only thing that I'm going to remind you is that work out the unit analysis. In this case, you have joules times second, all of that square. Mass of the electron is in kilograms times meter square. So let's do the unit analysis. Joule times second square. Then the second square, you can put it down as the denominator of this expression in the denominator. And this one, if you notice, that's the units for joules. So you have joule squared divided by joules, gives you the energy in units of joules as we had written it before. So we are done with this problem, and I hope that with these, and when you check out the video for benzene, you have a clearer picture of how to use this model for these type of systems. I'm signing off. Let me know if you have any questions, and have a good one.